Hello everyone, Mr. Cummings here, and welcome to this video on representing motion with tangent lines and secant lines. So first we're going to take a look at what exactly is a tangent line in a graph. So a tangent line to a curve is a straight line that touches the curve at a single point and nowhere else. When we use this with graphs, the slope of the tangent line at any given point is going to approximate the slope of that curved graph at that point. So we have this curve here, and at point P, if we were to draw a tangent line to that point P, we would take a straight edge or a ruler, and we would line that up so that it just touches the curve at that point, and we would draw a straight line using that straight edge. So the pink line here is indicating a line that is tangent to the curve at that point P. So now I'll take a look at an example with a data set that was plotted in graphical analysis. So this data set shows that an object is accelerating over time because we have a concave up position versus time graph. And we want to draw a best fit line, or a best fit tangent line, to the curve at time t equals 3. So we made a little dot at time t equals 3, and then we'll best fit our ruler so that we get a line that approximates the slope at that point in time on the curve. So the next thing we want to do is we want to calculate the slope of the best fit tangent line at time t equals 3. We're going to do this by picking 2 points on our tangent line, and we'll approximate these just by picking points that line up closely with x and y values. One of the points we know is 3, around 18. And then the other point we'll just pick, and then we will use those 2 points in the slope formula to calculate the slope of our blue tangent line. And we get that the slope of this blue tangent line is approximately 13 meters per second. When we include the units in our mathematics, we get meters divided by seconds. And if we note here that these are the units of velocity. So the slope of this tangent line is telling us something about the object's velocity. And that brings us to our next point, which is that the slope of the best fit tangent line to a curve approximates the instantaneous velocity of the object at that point in time. Because the position time graph is curved and the slope is always changing, by taking a tangent line to it, it gives us a snapshot of what the slope is at that point in time and allows us to get a rough estimate of what the object's velocity is at that point in time. So we're not going to calculate any more slopes. Instead, what we're going to do is we're going to take a look at best fit tangent lines at different points in time, just to visualize what is actually going on in this position time graph. So you already know it's speeding up, but we'll see if the tangent lines can help reinforce that idea. So we're going to draw a best fit tangent line at time t equals 3, which we've already done. Then we're going to draw a best fit tangent line at time t equals 1 and time t equals 5. And by looking at these slopes, we can see that the steepness, or the value of the slope from v1, v3, and v5 is gradually getting steeper and steeper, or it's getting bigger. So what that tells us about the velocity over time is that the velocity is increasing in the positive direction. So the speed is getting faster, and it is getting faster moving forward. Now we'll take a look at secant lines on graphs. So secant lines on a curve is a straight line that connects 2 points on the curve. So if we take a curve that has point P and point Q, and we draw a line connecting P and Q, that line is secant to the curve between points P and Q. And what this is going to tell us is it tells us the average slope of the function, or the curve, between those 2 points. So we'll go back and we'll apply this to the same data set that we had earlier, and we're going to draw a secant line that connects time t equals 0 to the position at time t equals 6 at the end of the graph. So now that we have our secant line drawn from time t equals 0 to time t equals 6, we want to calculate the slope of that secant line and include units in the calculation. Now, luckily, the way that the secant line is defined, because we're picking points that lie on the actual position time curve, we know these points pretty definitively. So we know the graph starts at the origin, 0, 0, and we know at time t equals 6 seconds, the position is 72 meters. So we'll just use these two values to calculate the slope of the graph and then figure out what that tells us about the object. So we get that the slope has units of meters per second again, because it tells us something about the velocity. And because we took the total displacement over the total time by calculating the slope of the secant line, we're getting an indicator of the object's average velocity over these 6 seconds. So the slope of a secant line between 2 points is just indicating the object's average velocity for that time interval. So to recap and to go over some takeaways, if we use best fit tangent lines on curved graphs, those graphs tell us, or they approximate, the instantaneous slope at that point in time. For a position time graph, the best fit tangent line is going to tell us the instantaneous velocity at that time. And remember, it is an approximation. If we take a secant line between 2 points on a position time graph, that's going to tell us the average slope of the graph between those 2 points. So for position time graphs, it tells us the average velocity between those 2 points. And as a small note here, we've drawn, as an example, we've drawn a secant line between time t equals 0 and 6. And we've drawn the tangent line to the point t equals 3. And we can actually see that these two have the same slopes. They're running parallel to each other. So what this tells us is the average velocity over the entire course of the 6 seconds is actually going to be equal to the instantaneous velocity at half of that time, so at time t equals 3. So there are times where the average velocity is going to equal the instantaneous velocity, and that ends up being at the midpoint on these parabolas. That's going to be it on this video on representing motion with tangent lines and secant lines. Thanks for tuning in, and I look forward to seeing you next time.